Yep. Good. I can turn the screen a little bit.
Okay, so today we have Miguel, who's been from McGil, and he's gonna tell us about the lambda singularities and electrolysis.
Yeah, thank you very much. So the talk will be about putting these two different topics and try to learn a bit about Feynman diagrams using ideas from some circuits. So the main object I'm interested in is the amplitude. Let me just write it as a big globe. The scattering amplitude is the function of many momentum, P1, P2, P4, all the way to Pn. This is a function in the complex plane of these variables. And the question I'm interested here is, so for which values of this argument, yeah, J is the amplitude singular. And of course, in equation theory, the amplitude is just given by a sum of many Feynman diagrams, bubbles and boxes. And so before I tell you why you should care about this, let me just state the main work on this topic. So in 1960, Landau wrote a paper where he wrote down a set of algebraic equations, and if you solve those equations, they allow you to find singularities of Feynman integrals. So, 1960. So this result, basically, this set of equations allow you, if you solve them, you find the singularity of Feynman integrals without having to solve for the integral. So we can study the singularities of them, and let me tell you why this is an important study, to determine these singularities. So let me just say by words. So in the 60s, people were interested in this because of the S-matrix bootstrap. So at the time, we didn't have HCD, so people tried to write dispersion relations. So most of the work has been like at one loop with massive particles. It's already very difficult to solve these equations. So that was the point back then. Then in the 70s and the 80s, with the integral models, when you impose a set of constraints, and then you try to find some S-matrix, people find some weird poles, and people then understood that these were related to some Landau singularities of triangle diagrams, boxes, etc. And in the last 20, 30 years, as we found the need to solve for these integrals, now involving massless particles, with the advent of on-shell methods, it became again interesting to try to solve for the singularities, because there is a relation between these singularities and the symbol of Feynman integrals. And so today there is basically a subfield of amplitudes which is basically worried about finding these Landau singularities or trying to solve these equations. Okay, are there any questions here? Yeah.
You're working Feynman diagram by Feynman diagram because your question is about the full amplitude, right?
Yeah.
But
so
we know that like there are certain singularities that
Yeah.
appear in individual diagrams, and then just cancel for physical quantities.
Yeah, so that's a good question. Yeah, that's a good question. Is so am I interested in the singularities of the full amplitude or the Feynman diagram? You could already ask that question in the 60s. Why did people? So if people wanted to write dispersion relations for pion scattering, why did people care about studying individual diagrams? So this set of singularities, which are called Landau singularities, which are the ones that appear in the individual Feynman integrals, we expect them to also be there in the full amplitude, because these correspond to like just having particles becoming on shell, like I have enough energy to produce a given number of particles. So these type of singularities you expect also to appear in the full amplitude, and people have some checks using other methods that.
In the fixed order, right? The set of singularities the amplitude has should be a strict subset of the number of the singularities that I'm in integral set. There could be less. I mean, there's dropouts, and we know we have explicit examples where there's dropouts of singularity.
Yeah. So okay. So if I study a division of, okay, yeah, your question is the other way around, indeed. So if I study some finite integral, it does not guarantee that this singularity is a singularity of the amplitude, but that's because you're in a specific theory. So if I change the couplings, I've changed my spins, numerators, etc. In general, I expect the singularity to appear. So indeed, I'm worried about studying these finite integrals in the genetic theory, and then finding all possible sets of singularities. Yeah. So yeah, are there any other questions here? Okay, so yeah, so the talk will be basically two parts. So first I will review these Landau equations. I will give some examples at one loop, and then I will present basically the main idea of using these techniques from circuits to try to solve these Landau equations in a recursive way. So the reason why I'm going to insist a bit on the review part is that if you know how to solve the one loop Landau equations, then you can recurse these techniques, and then in the end you always end up with a one loop set of Landau equations to solve. So if you are very good at solving one loop Landau equations, then it should be good to solve a bit more, yeah. So the set of equations where you have more loops. Yeah. Okay. So yeah, with that, let me. So if you write an integral, so the basic question is we want to understand when an integral, a function which has an integral representation, can become singular given the singularity of the integral. That's basically the basic question. Okay. And the main point is that f of s is singular when singularities, the integrand trap or pinch the contour of integration. So if I draw in this x plane where I'm integrating, I have some contour gamma, and I'm integrating, and then here I can put some singularities of I. This is when I becomes singular. Some particular values where there's a blow up, and then in general, if the singularity crosses the contour of integration, I'm able to deform this contour of integration. So in general, the function can develop some branch cut, but in general, it will not be singular because I'm just able to define another function, which is just a simple contour deformation of that one. But the cases in which I cannot do that are the cases where I expect f to develop a singularity. So this can basically occur in two ways. One is I just go to the endpoint of the integral. So I take one singularity, I bring it to the starting point of the integral, and then I cannot really deform this contour anymore. And that's called the endpoint singularity. And then the other cases is I need a pair, at least a pair of them, in which I bring this singularity somewhere, and there's another singularity that comes along and pinches or traps the contour. So this is what we call the pinching singularity. So let me just give a very basic example. So example one. So suppose the function is given by an integral between 0 and 1 dx. This. So in this case, I would have a simple just contour. I integrate from 0 and 1 x. And now my singularity, my integrand has some singularity at some s, which I control. So whenever I take this s close to the contour, I can just deform it. But if I take it to the endpoint, I expect a singularity, and indeed we can integrate. And this just gives simple function. And indeed, when s is equal to 0, I have singularity. So f of s singular when s equal to 0 or 1. Any questions here? So this is simple enough. So let me just do another example. So in this case, there's only the endpoint singularity in this case. So let's try to complicate a bit more this integrand. So okay, let me save some time. Let me do the following. I think. And now I just change this integrand. Okay, so now I have two poles, and I have one here. So if s is here, for example, I could have 1 minus s here. And now I should have the same type of singularities when I take s to 0, if this goes to 1. So I still have endpoint singularities, but now I can pinch the contour exactly when these two poles coincide, and that's when s is equal to 1/2. Okay, so indeed, if you integrate, so we expect now f of s to be singular when s equals 0, 1, and 1/2. So this would be endpoint, and this would be pinching. And if you integrate, you just find here. So you could see explicitly that this is the case. Okay. So any questions here? So now we're going to complicate by a good chunk. So now the next example I will consider is a generic Feynman integral. So a generic Feynman integral I can write, well, it depends on all my pi pj's. Okay, so then I have an integral over all the momenta, the loop momenta, J, L. And then I can also introduce some Feynman parameters to put all the propagators together. So L is the number of loops, P would be the number of propagators. These would be something like alphas over some denominator, E. And now D would be given by the sum of these factors of I, J, minus J squared. And so there's going to be L loops and a smaller number of propagators, of course. So it means that some of these momenta are depend on each other. So in practice, I have just write kj. So kj bigger than L is will depend on kj smaller than L. So these would be what I call loop momenta, which are the variables that are being integrated over. So now I want to do the same thing. I want to study when this integral gets divergent. I want to apply the same principle, which is I look for the singularities of the integrand which trap or pinch the contour integrator. So this is from 0 to 1. Trap or pinch. So for the Feynman integral, this is very easy in this context because there's a single denominator. So all I have to do is look for the zeros of this denominator and then see when they coincide. So I just need to ask for a double zero. Okay. So this gives me a necessary condition for the integral to be divergent. So the pinch occurs when you have a double zero. So a double zero would just mean I take the equal 0 and I ask for the derivative to also be 0. So there you go. And I ask with respect to all my variables. So that would be aj. So these would be just the loop momenta, the ones that are independent. Okay, so now I can do this. I know explicitly the formula. So I can just apply this to this. Okay, so we'll just draw. So these would be the set of Randall equations. Randall equations. Will be, so for example, this one, if I take derivative, since it's linear, it will just imply that all of these momenta are on shell. Right? So this one will tell me that kj squared is equal to mj squared. So on shell. And then this one is a bit more tricky, but the point is that I have all the momenta here. The point is that I'm summing over all the momenta, which are all the internal legs, but only a few of them are independent, right? So the kj's with j bigger than L will depend on the other ones because only a few of them are independent. So once you do that, you find the formula of this form. It's a bit messy here. Let's write like this. So the full set of equations will be and then I will have a sum over all the j's for each loop, and I sum over alpha j, aj in that loop. The sum must be 0. So basically, when I take a derivative, it will only act on the ones which depend on the same loop. So for each loop, I will have an equation, a linear relation like this. And then, of course, I must have a momentum conservation at each vertex. So I also have momentum conservation at each vertex. So this is what Landau wrote in 1960. So you see that it can get quite complicated. You see that if I have a big graph, then the number of equations will be really a lot. I will have like all these momenta are 4-dimensional. I have alphas, I have k. So it's easy to see that as we expect, Feynman integrals are hard to compute, and the Landau equations are also hard to solve. So it's not surprising. So yeah, I think it's better to just a few examples, and actually these 2 examples will be useful later. So are there any questions at this point?
You mentioned a double sort of zeros. Is there, if it's, could there be just and pick the triple zero?
Yeah, it could be triple zero. That will give you another constraint. It will give you like the second derivative. But actually, you know, the double zero doesn't mean that that is a singularity, because double zero just tells you that there is two singularities that meet at some point. But it doesn't tell you like they could meet, they could come from here and then they meet here at the top of the contour. It doesn't guarantee that there is singularity. It's a necessary condition. But indeed, as Enrico was saying, it might appear that there is singularity, but then by some cancellation or some particular thing or adding other diagonals, it's possible that all these get cancelled. So it's just a set of necessary conditions for a singularity to appear. But in principle, if you are able to determine all of them, you know all the possible ways that the amplitude can be singular. Yeah. So, okay, let's do just two examples. So let's do the bubble example. So this would be a simple diagram. So say I have some momentum P1, P2, K1, and some parameter alpha 1. Then I have some momentum K2, some P3, P4. So now the set of Landau equations will be simple. So I have, so let's say all the masses are 1, so M1, all the masses are 1. For simplicity, so I have K1 squared equals to K2 squared equals 1. And then I have the loop momenta, the loop equation. So I have, well, momentum conservation, let's say P1 plus P2 equals to K1 minus K2. And then I have alpha 1 K1 plus alpha 2 K2. Okay. So now the standard thing to do is to take dot products of this equation. So I can write it in a matrix form. We write it as K1 squared, K1 dot K2, K1 dot K2 squared, 2 0. Now, well, I have to make dot products appear because I know the answer. So this will be a function of S, and S is P1 plus P2 squared. So I must make the invariants appear, right? So this is the first step. And then I know already that the diagonal is fixed by the on-shell condition. And then I can also use this relation to fix the off-diagonal piece. So if I take the square, on the left I will have S, and then I will have S plus 1 plus 1, which is K1 squared plus K2 squared minus K1 not K2. And this fixes K1 not K2 to be 1 minus S over 2. Okay, so then I have everything to insert in this matrix. Then I have this is equivalent to 1 minus S over 2. Alpha 1, alpha 2. And now I want this linear system not to give me a trivial solution for alpha 1 and alpha 2. So this means that I want this matrix to not be invertible. I want the determinant to be 0. So then I have a relation 1 equals 0. And this gives me two solutions. Gives me S equals 0, well, S equals 4 or S equals 0. Okay, so if I restate the mass, this is just 2 times the mass squared. So this tells me that the bubble integral, when you compute it, whatever the answer is, must have these two singularities. So this is just the singularity for putting these two particles at rest. So they just produce at rest. So this is the normal threshold. And this is called the pseudo threshold, and it typically appears on the second sheet of this function. So yeah, so this is just a simple example. The question is here. Okay, so now we're almost there. In the interesting part. So let me just do the box, okay? And then, so with these two, so this is important to keep in mind. Let me put it here to the side. So S. So this is singular when S is equal to 0 or 4. So when all the masses are 1. The box. Another box will be a function of two variables and the masses, which we set to 1. One. So this will be function of 1 plus 2 squared. 1 plus 3. So now I want to find the locations for which values of S and T does this become singular. Okay, so I have, again, I have momentum conservation at each vertex. Let's say all the masses are 1. So I have the loop Landau equation, which will be just, we only have this loop. K2, K3, K4. So 0, I do the same idea. I take dot products. I write this as a linear system. Then I have K1 squared, K1 K2, K4. So it's a symmetric matrix. So we'll write the lower triangle. This will act on some vector 4. And now, as before, I just start fixing all these entries by using momentum conservation and the on-shell condition. So all the diagonal will be 1 because we have just all the masses are the same. One. And then I go to the corners. So K1.K2 here, I could fix using momentum conservation at this vertex. So for example, K3 will be K2 minus K1. And if I square this, I will get 1 plus 1 plus 1 minus 2 minus K1 K2. So this will fix me K1.K2 to be a half. Okay, so and then you keep going and you fix the other one. So I have 1/2 here. Then I have another corner, K2.K3 will also be 1/2. And I have K3.K4 half. And then K1.K4, it's 1/2. And then finally, I have K1.K3 and K2.K4. These ones are a bit harder because K1.K3, they do not share a vertex. So what I can do is I use momentum conservation in this volume, right? And so what I have is similar to this. P1 not P2, P1 plus P2 equals to K1 minus K3. So I square this. I have S, and I have 2 minus 2 K1 by K3. And then I fix K1 by K3 to be 1 minus S over 2. So then I finally complete the matrix. So this will be 1 minus S over 2. And similar for this one, you do the same thing, but what you're going to get is T. So S is the energy coming here, and T is the energy coming in this channel. So then I will get 1 minus T over 2. And then I take the determinant. And so take the determinant of this. And then this will give me a relation which will be S minus 4 equals 4. And this is basically the leading Landau singularity of this diagram. So if I compute this integral, which is hard, it involves masses, I know that it will have the singularity in this surface given by S and T. Okay. So you see how tedious this is just at one loop. So imagine doing this at higher loops. Okay. So at higher loops, so okay, so that's with this. So are there any questions here or? This is all very simple, just a linear algebra. Okay, so in general, I put here on this side, I put the case where I have the box, but I have one of the legs to be genetic mass. So it's the same story. But now these dot products will depend on the mass, right? Will depend on S and T, but also the mass. Okay, this will be useful because then when I recurse it, I will be able to show that higher loop diagrams I can reduce to this effective mass, where this mass will be a number which will depend on the energies of the sub-diagrams. So that's basically the idea. Okay, so let me just tell you, before going there, let me just tell you what happens at higher loops. So what is the way that people currently attack this problem? So what do people do today? So there's a whole field of mathematics that is worried about solving linear systems of equations, right? So basically the most successful method goes by the name of principal Landau experiments. And this is a work of Sebastian Montellen. So this is the most recent paper, is 2023. So this is a package you can download. So the basic idea is that, so a basic result is that if I have a linear system of equations where the starting point are just all of these variables have some rational coefficients, then the end result will also be a polynomial with rational coefficients. So the main point is that you write an ansatz. So I have for some amplitude that depends on pi, pj, some genetic kinematics. Just write the most general form. So for 2 to 2, this will be just S and T. That's going to be I and J. And then I have also to sum over some masses, Mj. And then, so this would be my general Landau equation. And I have some powers. I have some higher powers here, which I have to sum over also. And M. Okay, so in the end, you will have like, basically you write the most generic polynomial up to some degree, and then you have these coefficients, which you know will be rational. And then what you do is you solve these equations numerically. So you do numerical fitting. So you fix some kinematics, and then you solve this equation many times for different numbers, and then you use methods of algebraic geometry to reconstruct what's the polynomial. Okay, so this approach. So actually, we're trying it with Simon and Matteo, and we were surprised actually how fast it starts to struggle. So the moment you add more kinematic scales, higher points, more masses, you really need a cluster. So you need to put a cluster for a weekend just to solve like a 2-loop example. So it's. But there are other diagrams in which it really excels, and those diagrams are the ones in which this recursive approach struggles. So I want to get to that. Okay, so
can you repeat the statement? So you solve linear equations.
Yeah.
And you don't care that there's like all these k-squared, there's quadratic equations mixed in.
Yeah,
because we have this ki squared equals m squared.
No, they're all quadratic, right? So this, I mean, yeah, these are. So I mean linear. Polynomial. Sorry. In this case, this loop equation becomes a linear system in these invariants, but in general, it becomes a higher degree. Yeah, the for one loop is just a simple linear system of equations. So I mean, I dotted the momenta, right? So it becomes essentially quadratic in the momenta, but my variables are these quadratic invariants. So in this case, it becomes a linear system, but you know, higher loops, it becomes way more complicated. Yeah. Okay.
Always about on up basically the down distributed. So just that you have more scales.
Yeah.
But they're just more parameters to solve.
Yeah, precisely. Yeah, more scales. Like if you have more endpoint, like if you have an endpoint amplitude, the number of invariant scales quadratically.
These are external scales.
Yeah, you have external.
It's like really well for 4 points.
No, not even for one. Like if you have all different masses, then it's a problem. If you have all of these have different masses, but all I'm saying is that yeah, higher loops you have more masses, higher points you have even more because they scale with a square. You have all the pairs. Okay.
How high a polynomial do you have to go? Like, so can you just for some examples, can you show some numbers of how?
Yeah, I will show some numbers, like a higher, more complicated example. Yeah, but yeah, I mean, we have an understanding. I mean, part of this work was to understand if there is like an upper bound on the, like given a diagram with a number of loops, do I know the maximum degree of this polynomial, for example, and then I can start my study. So yeah, so we know. I mean, you expect that this is the case, right? If I have that this polynomial cannot have a very high degree if the diagram is small. Yeah.
But Sebastian's point has this some heuristics built in, or is there some assumption that
Which assumption that
the degree is higher? Like if there's another zero somehow, like you can take whatever.
No, he knows the formula. He knows there is a degree. We know. I don't know, but I don't remember. But we know that exactly how the bound on the degree is. So
That's what I was wondering.
yeah, we know that. So then you can go. But yeah. Yeah. So okay, let me go to the interesting, more physics part. So let's go. So let me just remind you of, let me show you a picture that you probably haven't seen in a while. So suppose I give you some potential difference here. And I tell you there are some resistances here. Two. And then I ask you, what is the current that flows in this line? And the answer is the current will be given by this potential difference over some effective resistance. But R bar is just a well-known formula for additional resistance in parallel. And so basically, what this entails in a graph theory way is that I'm able to reduce this circuit to an effective circuit with an effective resistance. Okay, so in terms of finite diagrams, I reduced from 2 loops to 1 loop. Okay. So I want to try to do the same idea in finite diagrams. Okay, so let me just write a table now. So on one side, I have electrical circuits. I have finite diagrams. Okay. So for the current, I have a simple analogous quantity, which is the momentum. Okay. And one difference is that this momentum is for them is d-dimensional, and this is just a scalar quantity. And this momentum in particular, the modulus, its length is constrained by some mass. Okay. And then I have resistance. And the equivalent quantity is this alpha parameter. Okay? So this alpha, another way of seeing it is as some kind of proper time of this particle. Now we'll go a bit more into this. And the other quantity, well, just Ohm's law, I have the potential difference is R times the current. And if I multiply these two, if I see this as a proper time times momentum will give me some space-time displacement of X. Now, with these analogies, then I can make a really good, well, I can translate this the Landau equations in terms of circuit laws. So these are precisely the Kirchhoff laws. Law. This is just momentum conservation at each vertex. So I just actually had to look up this right before the talk because I didn't remember exactly what it was. So this is just the current being conserved at each vertex. Right? So, and then we have the Kirchhoff second law, which tells you that the potential difference across the loop is 0. And this is precisely the loop equation. This just tells you like that's just the Landau loop equation. It just tells you that the total space-time displacement is 0 across the loop. So if I sum all these alphas and k's, so this is just telling you that basically Landau singularities are just when classical propagation happens. So when all particles are on shell, and basically I have some loop here, and I'm telling you that the delta x of going from here to here is the same as the delta x of the particle going from here to here. Just telling you that all the particles propagate on straight lines, classical trajectories. Yeah. Okay, so with this analogy, so the interesting part, the punchline is basically everything that I can do with circuits, I should be able also to do with Feynman diagrams, with the Landau equations, because basically all these rules apply here. The difference is that Feynman diagrams have like the momenta are d-dimensional, and I have some additional constraints, but in principle I should be able to use similar ideas. Okay, so let me just give an explicit example. Well, let's consider a two-loop graph, which reminds a lot of this circuit. So this would be, for example, this diagram. So I have some K1 going here, K2, alpha 2 prime, K2 prime, alpha 3, K3. So for these, the Landau equations are simply two-loop equations. I have one loop here, and I have the other loop. So I just have 1K1 plus K2. Then I have K2 minus K2 prime equals 0. So now what I can do is I can solve for one of these loop. So I solve, for example, this loop, this loop equation. I insert it back, and I can write it in the following form. I can write it as alpha K1, alpha 2 bar, K2 bar, 3 K3, 4 K4. Okay. So what are the differences? So K2 bar is the sum K2 plus K2 prime. So it's the total momentum flowing here. So this would be K2 bar, which is the sum of these momenta. And then I have an alpha, the Q bar, which is given in terms of the individual alphas, alpha 2 and alpha 2 prime, sorry. prime in the very recognizable form. Okay, so I'm basically able to reduce the analysis, the Landau analysis of this diagram to the Landau analysis of a one loop diagram where I have a new edge. Okay. And so now here in this new diagram, I have a flow of alpha 1 k1, and I have alpha 2 k2 bar. So okay, I reduce this equation. So I reduce this equation to some loop equation of this diagram. But now I also have, and this is the interesting part, it is the fact that here all these momenta have the mass, they are on shell and they are related to the mass, right? But here I don't know in principle, right? I don't know what is K2 squared. Sorry, what is it? But this effective edge here, if I zoom in, what it looks like, it actually looks like a bubble. Right? Here. So K2 squared is simply the Landau singularity of the bubble, right? It tells me the mass, or basically so K2 is this. So this is just tells me when does the momenta, the total invariant, the total energy that comes here give rise to a Landau singularity. So basically I'm able to, in other words, I'm able to separate the problem into have a two loop equation. I write one loop equation for an effective diagram, and then everything else is the same except that the mass of this edge is now fixed by the smaller loop diagram, right? So that's the recursive nature.
So this analogy to the Kirchhoff's laws that's been known since
Exactly.
1960s. So what's I can't remember exactly.
Yeah.
What's new, like this stuff, this recursive idea.
Yeah.
Was that from the past? Or?
Yeah, that's a good question. I don't know why people didn't think about it. Or at least I don't know why I haven't found it yet. I mean, so this analogy with the Kirchhoff law is known and it's in the books.
Yeah, I think Bjorken and Drell.
Yeah, exactly. No, it's in the books. But yeah,
But this basic idea of replacing the resistors.
Yeah.
With an effective one.
So
you don't know where it is. Or...
So so I don't know why. So one thing I can say for sure is that today no one knew about this.
Yeah.
So the other thing is what I can say is that I can try to think of why people didn't pursue this idea in the past. So basically, one crucial thing is that this gives me a relation between the alphas, but the alphas I don't really care in a practical. They are auxiliary parameters. What I do care is the fact that I'm able to see this as a new diagram with a new effective mass, and here it's quite easy. I mean, here is there is no big surprise that I can just I'm able to replace this mass by something that has like twice the mass, right? So these I'm just using the Landau singularity of the bubble, which I erased, which we derived before. It had two solutions, was 4 or 0. And if I'm able to plug it here, then I find the two possible singularities of these two loop diagrams. In the past, people were not really. I don't think people really cared about computing Landau equations to the full extent. What they cared more is like which singularities are on the physical sheet, because that's what allows me to write the dispersion relation. So they were really focusing on like one loop cases with masses, and then studying carefully where the singularities come in the physical sheet, cross branch cuts, etc. So the study was not so much about heavy computation as it is today. It was more like understanding a bit more. So yeah, so okay, let me just give you a better example where it's less trivial. So that would be, for example, the double box. So this double box, let's do all equal masses. Okay. So I have all these different momenta. I mean, yeah, I should say, I don't know if who was in amplitudes here. I guess some of you probably went to Matthew's talk. So in this first paper that we had a different approach. We were thinking about taking cuts. So that approach had a problem, which is it only allowed to go with 2 particle cuts and didn't give you any information about the alpha, which people care also. Alphas, the sign of the alphas tells you is related to the position where it is in the symbol. It's kind of an open problem. So in this way, which is actually more closely related to the lambda equations, we don't know why we didn't see it wrong. We didn't think about this. We have to go through this cut idea using unitarity to arrive at this very simple formulation, which is equivalent. So basically, if I write this. So I have 2 loops here, and it starts to become a bit more complicated. So I have basically a set of alpha 1 k1, sorry, alpha 1 k1, that's alpha 1 prime to b prime. So alpha 2, 2, it's alpha 3 k3, alpha 4 k4. So these 2 loop equations you can manipulate. You can write in terms of a single new diagram, basically. Similar story. Okay. And now you have a different alpha 1 bar. You have a different alpha 2 bar, k2 bar. You have a different alpha 3 bar, k3, alpha 2, k4. Okay. Okay. So then you find the formula. You find a simple Landau loop. 1. Okay, so what are the formulas for these alpha bars? So alpha 2, so k2 will be just, again, the sum of momenta, k2 plus k2 prime. So alpha 2 bar will just be given by alpha 2 prime, and then you have a sum over all the alphas that are in this loop that you solve. And you have alpha 1 bar 1 plus alpha 1 prime alpha 2 prime. So alpha 2. Then I have bar. P prime, just a bunch of equations. So these are the effective alphas or effective resistances after you do this reduction. So now let's just do a simple check, which is just simple check. Let's take these alphas to be 0. That means I'm contracting this graph. So I take alpha 1 prime equals to alpha 3 prime to 0. I should be able to reduce the previous formula. Of course, indeed I do. This alpha 2 bar, well, this goes to 0, this goes to 0, so I just get alpha 2 bar is equal to alpha 2 prime, alpha 2 prime, which is just the sum of effective resistances in parallel. And then I have, if I take alpha 1 prime to 0, I just get alpha 1. So I just get back to the previous case, and then alpha 3 bar, alpha 3. Okay, so it just shows as a consistency check that we get back to the previous case. The other check, the final check, before I stop, is to do, for example, let's take, so if I see this as some resistance, let's take alpha 2 to be very big. So effectively, I'm taking the proper time of propagation of this particle very large. So effectively, there is no propagation here. So if I take alpha 2 very big, I'm essentially deleting this edge. And indeed, if I take alpha 2 to be very large, just, sorry, I think I mixed up here. Yeah, this is alpha 2 here. All the ones in the loop. So if I take alpha 2 very large, it just becomes alpha 2 prime. I just get alpha 1 plus alpha 1 prime here. Prime. So basically, I delete this edge, and then I just get a sum of resistances in sequence. Here, the same thing, and here is the previous case. Okay. So this is just a play, just a game with resistances, right? So what's really the okay? So this formula for the alphas will be interesting because if I'm able to compute the previous alphas, I can find the new ones of the new diagram. So what's the interesting part here is that, so I look again at this edge. So to determine the Landau singularity, I look at this edge. And effectively, this edge is given by some box diagram, right? So this K2 momentum here is basically, so K2 squared is basically the T in this diagram, right? So this tells me that to solve this Landau singularity of this full system, I need to solve this box, but now all these particles have mass 1, but the mass of this particle is given by the T Landau singularity of the box. So that's the recursive point, is that this will be T of the box, which will depend on S. And the T of the box we determined before, right? So we determine it satisfies this equation. So this will be my mass. So now if I plug this in this formula here, depends on the mass, then I get a new relation. And this will give me a higher degree because you see if M now depends on S via this formula, so this will be M squared. Now I'm going to get a higher degree polynomial here, and that's exactly the double box Landau singularity. So this, if you use a PLD, for example, that package, it will take, like, for example, 1 day to find this Landau singularity, and we have it immediately, right? Yeah. So
are there cases where the recursive way runs into trouble?
yeah, exactly. So this is all so far also good news. Everything is good news. So, so where are the trouble? Let me just mention.
That's about the double block.
Yeah.
So. This is the box also has the external singularity as well.
Yeah.
So it seems like I could have pinched the box this way, but I also could have pinched it this way.
Yeah.
And had like some dangling tree that has a red line attached to the left side.
Exactly. So all these possibilities, exactly. So in the end, so it's very interesting because this recursive way, like, okay, this box itself, it has multiple singularities. I'm just showing one. It's the leading singularity, which is the max cut, right? But it has all the different. So all these ways of breaking this graph down, like in all the different contractions, will give you all the possible branches of the polynomial. So it allows you to also organize the calculation. So let's say I'm interested in the Landau singularity. Just go and do exactly that in sequence. So, okay, so time. So let me just give one example of something that we can do now, we could not do before. So I mean, there's several examples, several diagrams we computed that are relevant for the standard model. So for example, this pentabox here with all different kinematic scales. These are in total 13 scales. This is like a 30 megabyte polynomial. It's on GitHub. So this one is like so with this huge, sorry, it's 18 scales. So with this huge amount of scales, we could not solve it with the other method. one example, which I want to do explicitly, like, so in a previous paper we had with Sasha and Amit, we were studying this diagram. This diagram is a diagram which has no two particle cut. It's all four particle cuts in each channel. This is a diagram which is relevant and was studied already in the 60s by Gribov's book. So Gribov's group. So it was Kolkunov, Hudik, Okun, and Sudakov. So this was relevant for pi scattering. So now we can determine this. So when I was studying this, I did this numerically. So analytically now it's very easy because I can just see that this diagram here in the middle, so it's non-planar, this is just a box that is hidden, right? So then I can reduce this to a simple thing. Right, and now I can reduce each of these bubbles to just a single edge, right? With twice the mass. And then I'm back to the double box, which I already know how to solve. So the formula for this Landau singularity is s minus 16 cubed t squared minus 4 s minus 16 cubed t minus 16 32 plus s squared minus 10s squared. So just all the masses are one here. Okay. So this all seems very good, but there are some limitations. Let me just say. So we can do very big graphs, and for example, Sebastian's package struggles when you add scales. But for us, the most difficult diagram is just this simple diagram here. This diagram is what kills us. Because one thing I didn't mention is that all these ways I was doing it to give me immediate answer. So I was able to solve all the Landau equations in a sequence, right? But for example, here, this diagram here, the pentabox, it depends on the order in which I reduce it. So if I do first this loop, then this reduces me to a simple diagram, like simple pentagon, right? With a different mass. I know how to do it. But if I do it the other way, I do this first, then I find something like this. Okay. But now two legs are different. And now the Landau, so each of these legs, they don't have a single equation for each. There is one equation that relates the two. That's because the Landau singularity is a codimension one surface. So I will have an additional variable that is not fixed by reducing these pentagons. So this is what happens when you deal with higher point diagrams. You have additional variable that you cannot fix. And the way to do it is to take extra derivatives. So for each higher point diagram you reduce, you get additional edges whose masses are not fixed individual, but are related to each other. So I have some equation that relates the masses of these diagrams. I don't have one equation for each edge. So this tells me that the recursive has some problem in which I have an excess of variables for the number of equations. So I have to take additional constraints which are involved in these alphas. So this is one way where the alphas play a role. Okay. So sorry, I'm really over time. So the problem with this diagram is that you do this and you get, it's the maximally case where you keep having edges. So if I, for example, reduce this case, this loop here, I will get something like this here. So I have two edges, one equation for both masses, and then I do the other loop, for example, this loop, and then I get something like this. Okay, and now I have some purple. So I have this leg here. So in total, I end up with three equations, which are not fixed. So they have three equations and they all degree 5. So we cannot solve them. So this, for them, this diagram is very good with Sebastian's package because this diagram is very symmetric, very few scales. So this diagram, you can just do it with this package, for example. So this is one case where we don't know. So that's the bottleneck for now. But we haven't, so everything we've done is on a laptop. So we haven't put anything on a cluster. If we try to put this, maybe we can do a similar performance as what he does. Yeah, so
given you have the information from Sebastian's package, you might think that you can fill in some missing information, or you can, if you're complaining that that it's in, I guess you don't have enough equations, or
Yeah, I mean, we have 3 equations for like 2 variables here, but all of these equations, each individual equation is a degree 5, so we cannot solve it exactly.
But on the other hand, there's already a solution from Sebastian,
Yeah,
so there must be some information.
no, there must be
By
like, so
reverse-
we can, I mean,
Reverse
what,
engineer something.
yeah, I agree with it. But what it does is like it puts the whole set of equations, like with the alphas, everything, and then it does numerical. So we have these algebraic geometry tools, and then it fits the polynomial in a way. So it basically kind of avoids manipulating all these degree 5 roots and everything. So it's kind of a black box. So, but yeah, I mean, we are working with Sebastian to try to put the things together, the 2 things together. So yeah, so let me stop here. But yeah, I don't know why no one has applied this. It's surprising. I know that at some point I'll find a paper from the Russians in the 60s that they did it, but at least no one knew today, at least they talk, so at least we are rediscovering knowledge, useful knowledge.
Yeah, I mean, so people talk about like loop by loop Markov parameterization,
Good.
things like this. So this, I mean, it's not
Good.
like with bubbles. Like if someone sees a bubble, they of course you integrate out the bubble first. You get a propagator.
Exactly.
Reduce the loop order. I mean, that's like, I mean, people do that all the time, right?
Hmm.
So
So,
it's
yeah. No, it's a very good point. So yeah, exactly. Indeed, I didn't mention it, but so what you could do is try to do a Landau analysis on the loop by loop Markov, and that's exactly what you're gonna land on. Like all these
people for massless graphs, people have done that, right? In the context of this classical gravity stuff, like Matthias Wilhelm and
what people have done, like Landau analysis. Yeah. I don't know. Like what I know is that indeed when I write this matrix form and this determinant that I wrote of the linear system, this determinant is exactly what appears in the denominator of the loop by loop Markov. So that's the Markov denominator. And if you do loop by loop, but for example, one problem with the loop by loop is that I'm not sure you know which order to do. Like which order is the most optimal one.
Okay, no.
Yeah, exactly. We have the same thing. Which order is it the one to do first?
Yeah, no.
Exactly.
No one else.
Yeah, exactly. So yeah, so the loop, yeah, indeed. So if you just do like the standard analysis of like when does integral become singular on the loop by loop, you're gonna end up on similar set of recursive equations. But one complaint we had, so this is something we are doing. One complaint we had is like, how do I know what you're doing before these cuts is actually a singularity of a Feynman integral? With the loop by loop, there's no question. We just write. In this case, we are connecting really to the standard Landau equations. So, I mean, we're trying to see which one is best, but I think it is kind of all equivalent with loop by loop. Yeah. Yeah.